In this video, we're going to expand our design space by giving our character the ability to climb. In video games, there are many different interpretations or implementations of climbing. You have the deliberate and designed climbing of Assassin's Creed and Uncharted to the free climbing of Breath of the Wild and Genshin Impact. In this video, we're going to create something similar to Ocarina of Time. That's not to say that we're aiming to emulate it completely, but it is a good example of what we're trying to achieve. Here, we see that young Link has several different animations depending on the height of the ledge. We have the hop for about waist high, the quick climb for about neck height, the climb where he struggles a bit at head height, and the jump to hang for above head height where you can choose to either climb up or drop down. Similarly, we'll have a step up, a vault, a climb, and a hang. Because the style of climbing that we're going to implement is not determined at design time, but rather at runtime, our character must sample the world around them and judge if they can climb or not. So before we get into it, I'll first explain the steps that are used to determine if an obstacle is climbable. Hopefully this will prime you for what's to come and help you understand the what and why when we do things. The first thing we need to do is to detect a surface. We do that by casting downward from a point above and forward of our character, and as the character moves around we may find something like this. Even though we can see that this should be climbable, the script does not, so we will need a few more checks. The second thing we're going to do is a forward cast, just slightly below the point of the downward hit. This is to sample the vertical surface of the ledge, which we'll need for later. If those two ray casts hit, then we'll do a third cast from the top of our character. This helps determine if the ledge is above the character and should be something that we want to walk under instead of climb, like a doorway or an overpass. Here is an example of where both the downcast and the forward cast hit, but the overpass cast does not, indicating not to initiate a climb. Then we have to check the slope of the ledge's surface to see if it's too steep or not, and we can do that by comparing the ground normal to the world up. Similarly, we have to do the same for the wall angle of the forward hit. This is determined how directly the character is moving into the wall. We only want to climb if that's the intent, and we use this angle as a measure of that. After passing the angle checks, we're going to apply an offset to the down hit point to move it inward, as normally it's going to be a point very close to the edge. We apply this offset as it will be our end position and we don't want to climb up only to fall back down. Next, we have to depenetrate the point. If I were to place the character's capsule at the end point, you can see that there is an overlap due to the ground slope, when it should really be tangent to the capsule's bottom sphere. Depenetration yields this new and final point. Now that we have our endpoint, we need to determine if there's space for our character. We'll do this by performing a capsule sweep, first up, then towards the endpoint. Quickly recapping, first, downcast to find a ledge. Second, we do a forward cast to sample the vertical surface. Third, we do an overpass cast to see if we should just walk underneath it. Fourth, we determine if the ledge is not too steep. Fifth, we check how directly the character is moving towards the wall. Sixth, we apply an offset to move away from the edge. Seventh, we depenetrate the point for our capsule. Lastly, we check for space by doing a capsule sweep up and forward. Now that you're primed, we can begin. We are starting at the end of the character controller, so none of the stances, and all I've done so far is update the project version. First, I'll import the event curator, the SMB events, and the editor for it. Then I'll set up the scene by creating ledges of increasing heights at increments of 0.5 meters. Then I'll move all the current animations into a new folder and import our climbing animations. And as usual, these can be found in Mixamo. I'll select all of them and set the animation type to humanoid, avatar definition as copied from other avatar, source as our XSplit avatar, and apply. Then individually I'll set the animation settings. Here you can see all the animations and their settings. Note that for a running jump, I've trimmed the clip to start at frame 23 and end at frame 85, as that's the part that we're interested in. Then, let's add all of them to our animator controller, and I'm going to change the names so they make more sense to me. Brace hang to crouch becomes climb up, running jump becomes vault, jumping becomes step up, and free hang drop becomes drop. Then I'll duplicate drop and name it drop to air. If you like, you can place all the climb animations under a substate, but I'll leave it like this. Anyways, let's create a transition from stand to free hang to hang idle, and then do the same from all the other animations back to base. I'll leave the transition settings as is, other than rounding the exit time to nicer looking numbers. Now with the animator set up, let's open our character controller script. First, we're going to need a reference to the rigid body, capsule collider, and a reference to the event curator. Then let's add a few serialized fields for our climbing settings. Wall angle max for how direct we need to face the ledges, ground angle max for the maximum slope a ledge's surface can have, and a layer mask for the layers to consider. Then, a float to represent the height of a ledge to be considered an overpass, a vector 3 to represent the origin of our downward cast relative to the player, and a private bool to represent if the character is climbing or not. In the start, we'll get references to the new components using getComponent. In the update, I'll encapsulate everything below the move input vector in an if not climbing statement. I correct it later. At the bottom of the if, we'll determine if we want to climb, can climb, and finally initiate a climb. In my implementation, I only want to climb if the player is both pressing the forward and if they're sprinting. Then I'll create a new function called canClimb, which returns a true or false, and I'll call it in the update. Obviously, canClimb will determine if our character can climb, and it will need a few things. 3 booleans to represent if each of our raycasts hit, the height of the ledge, the slope of the ledge, the angle that the character is running into the ledge at, 3 raycast hits to store the information of each of our raycasts, a vector 3 for the final position, a vector 3 for the character's forward direction projected onto the XZ plane, and a vector 3 for the normal of the ledge's vertical surface projected onto the XZ plane. Now we need to do our downcast. The direction is vector 3.down, and the origin is the transform point of the climb origin down to make it relative to our character. Down hit will be equal to the physics.raycast using the down origin, down direction, the climb layer mask, and we'll output the raycast hit into the down raycast hit. The cast only needs to go as far as the lowest ledge you can climb, so the distance is the difference between the climb origin down's y and the step height, which I'll add a serialized field for. If the down hit is true, we need to do the forward and overpass cast. The forward distance is how far forward the down origin is of our character, so climb origin down.z. The forward origin is where the character is now, but with the height set to just below the down hit point. I'm using an arbitrary 0.1. Similarly, the overpass origin is where the character is, but at the overpass height. Forward direction xz is the direction of our cast, and it is the transforms forward projected onto the plane defined by the normal of vector 3.up, in other words, the xz plane. Then the forward hit is equal to the physics.raycast, starting at the forward origin, going in the forward direction by the forward distance on the layer mask climb, and outputted to the forward raycast hit. The overpass hit is the same, except starting at the overpass origin and outputting to the overpass raycast hit. Next, we'll calculate the climb height by taking the difference between the y's of the down raycast hit dot point and the transform dot position. So, if the forward hit and if the overpass hit or the climb height is less than the overpass height, this extra condition is because everything below the overpass height should be an obstacle that the character can't walk underneath and should try to climb over. Passing those conditions, we need to check the angles, so we'll calculate the forward normal xz vector first by projecting the normal of the forward raycast hit onto the xz plane. Then we'll calculate the ground angle by using vector 3.angle from our down raycast hit.normal and the world up. And the wall angle is the angle between the negative forward normal xz and the forward direction xz. If the wall angle is less than or equal to the wall angle max, and if the ground angle is less than or equal to the ground angle max, we can apply our endpoint offset. Let's quickly add a serialized field for the offset. We want the offset to be relative to the ledge's surface, where positive z moves inward, away from the ledge. To get that inward vector, we'll project the forward direction xz onto the plane of the ledge's surface. Then we can calculate our end position by taking the down raycast hit dot point and offsetting it by the end offset oriented by the rotation defined with the forward of the surface vector and the up of the world up. Next is depenetration, and I'll start by caching the ledge's collider. Then, to see if there's an overlap, I'll use physics.computepenetration and I'll explicitly state the arguments so it's easier to see. Collider A is the character's capsule collider, position A is the end position, rotation A is the current rotation, collider B is collider B or the ledge's collider, position B and rotation B is collider B's current position and rotation. Lastly, we'll store the direction and the distance required to depenetrate the two colliders. If there's an overlap, we'll offset the end position by adding the penetration direction multiplied by the penetration distance. The next step is to do our sweeps, and we'll create a new function to do that for us. Character sweep will return a bool and take in a position, rotation, direction of the sweep, distance, layer mask, and an inflate, the amount to increase or decrease the size of the capsule used for sweeping. The character sweep will be used to check if there's room for our character, and it'll do that by using a physics.capsuleCast. Here you can see that the capsule cast requires the centers of the spheres at each end of the capsule and their radius. At first, that seems relatively simple as the capsule collider has several properties that we can use to either calculate or get them directly. However, these properties are in local space, while the capsule cast is in world space. So before we continue with our script, I'll take a moment to explain and visualize why you can't directly use the capsule properties. Here, I created a simple script where I naively calculate the top and bottom spheres of the character's capsule. I do this by starting at the capsule center and moving up or down, assuming it's on the y-axis, by half the height subtracted by the radius. At first glance, our spheres in blue match the capsule. But as we move the character, our spheres don't move with them, as the capsule is in local space and not world, so the positions don't match. The same can be said for rotation and lastly scaling. Here we see that the radius is 0.25, but that is relative to the game object. Another issue with this is the height, as the height we see in the inspector is not the height of the capsule. The actual height is whichever is greater, the height value or the diameter of the capsule. When they're equal, we can see that they're the same, but as we continue to reduce the height, the capsule does not shrink any further, and the height is actually the diameter. And, of course, the direction will have an effect, but let's just assume the y-axis. So let's make this better. Let's start by calculating the total height by taking the max of the capsule height and 2 times the radius and use that as the height in our top and bottom calculations. This fixes the issue of the height being less than the diameter and the spheres no longer invert. Now let's take a closer look at the scale. Again, this is in the direction of the y-axis. As we scale the y, the height scales. If we scale the x, the radius scales, and the same with the z, but the radius increases all 3 dimensions even if we only scale 1. Additionally, the radius is only scaled by the greater of the 2 dimensions. Here, x is at 2, and increasing z does nothing until it grows greater than it, then z becomes a new scale. In summary, we have to apply the character's transform, rotation, and scale matrix, but because of the ability to change the capsule's direction, we can't apply it directly using matrix multiplication, so we'll do it individually. First, we'll get the height scale by taking the absolute y of the transform's lossy scale. Then, we'll get the radius scale by taking the larger of the absolute x and the absolute z. And from there, we can calculate the true radius by scaling the capsule's radius by our radius scale. and the total height is the larger of the capsule's height scaled and the true diameter. The direction to move from the center is the transform's up, and the center position is the transform point of the capsule's center, moving it from local to world space. Finally, we can calculate the top and bottom. The top by starting at the center and moving in the positive direction by half the total height subtracted by the radius, and the bottom by moving in the negative direction. Back in the scene, our better red sphere matches the position, rotation, and scale. Now we can return to our character controller and use what we learned to finish the character suite. Let's just copy and paste over the code, and I'm going to rename direction to capsule up so we don't confuse it with the direction parameter. Additionally, it is no longer going to be transform.up as we don't necessarily want to check the current orientation, but rather the one passed in as rotation. So capsule up is equal to the rotations up, or rotation times vector3.up. Similarly, center becomes position offset by the capsule center in the passed in rotation. With that done, we can call physics.capsule cast. Point 1 as bottom, point 2 as top, radius as radius plus inflate, direction as direction, max distance as distance, and layer mass as layer mass. Then we'll return if the cast hit anything. Back in CanClimb, I'll make the inflate an arbitrary negative 0.05 to give the sweep a bit of leeway if we're pressed up against a wall. For the up sweep, the distance is the difference between the down raycast hit point.y and the transform's position.y. The direction is the transform's up, and the origin the transform's position. With all that, we can call our character sweep to see if there's room for our character to move up the ledge. Then we can do the forward sweep. The origin is the end of the up sweep, and the vector to sweep in is from origin to the end position. Using those, we'll call the character sweep again. Position is the forward origin, rotation is the current rotation, direction is the forward sweep vector normalized, distance is the forward sweep vector's magnitude, layer mass is the layer mass climb, and the inflate is inflate. Finally, if neither the up sweep and the forward sweep hit anything, we can return true. With all that said and done, our character finally knows if they can climb or not. But for now, we'll cut that there, as we were moving pretty quickly and it's a lot to take in. So take a break, let that digest, and I'll see you in part 2.